A comet is an icy small solar system body that, when passing close to the Sun, heats up and begins to outgas, displaying a visible atmosphere, a coma, and sometimes also a tail. These phenomena are due to the effects of solar radiation and the solar wind upon the nucleus of the comet. Comet nuclei range from a few hundred meters to tens of kilometers across and are composed of loose collections of ice, dust, and small rocky particles. The coma and tail are much larger and, if sufficiently bright, may be seen from the Earth without the aid of a telescope. Comets have been observed and recorded since ancient times by many cultures. Comets usually have highly eccentric elliptical orbits, and they have a wide range of orbital periods, ranging from several years to potentially several millions of years. Short-period comets originate in the Kuiper belt or its associated scattered disk, which lie beyond the orbit of Neptune. Long-period comets are thought to originate in the Oort cloud, a spherical cloud of icy bodies extending from outside the Kuiper belt to halfway to the next nearest star. Long-period comets are directed towards the Sun from the Oort cloud by gravitational perturbations caused by passing stars and the galactic tide. Hyperbolic comets may pass once through the inner solar system before being flung out to interstellar space. Comets are distinguished from asteroids by the presence of an extended, gravitationally unbound atmosphere surrounding the central nucleus. This atmosphere has parts termed the coma and the tail. However, extinct comets that have passed close to the Sun many times have lost nearly all of the volatile ices and dust and may come to resemble small asteroids. Asteroids are thought to have a different origin from comets, having formed inside the orbit of Jupiter rather than in the outer solar system. The discovery of main belt comets and active centaurs has blurred the distinction between asteroids and comets. As of November 2014, there are 5,253 known comets, a number that is steadily increasing. However, this represents only a tiny fraction of the total potential comet population, as the reservoir of comet-like bodies in the outer solar system is estimated to be 1 trillion. Roughly one comet per year is visible to the naked eye, though many of these are faint and unspectacular. Particularly bright examples are called great comets. Comets have been visited by unmanned probes such as the European Space Agency Rosetta, which became the first ever to land a robotic spacecraft on a comet, and NASA's Deep Impact, which blasted a crater on Comet Tempel 1 to study its interior. Etymology. The word comet derives from the Old English comether from the Latin comether cometes. That, in turn, is a Latinization of the Greek kappa omicron mu eta tau eta sigma, and the Oxford English Dictionary notes that the term kappa omicron mu eta tau eta sigma already meant long-haired star comet in Greek. Kappa omicron mu eta tau eta sigma was derived from kappa omicron mu nu, which was itself derived from kappa omicron mu eta and was used to mean the tail of a comet. The astronomical symbol for comets is comet, consisting of a small disk with 3 hair-like extensions. Physical characteristics. Nucleus. The solid, core structure of a comet is known as the nucleus. Cometary nuclei are composed of an amalgamation of rock, dust, water, ice, and frozen gases such as carbon dioxide, carbon monoxide, methane, and ammonia. As such, they are popularly described as dirty snowballs, after Fred Whipple's model. However, some comets may have a higher dust content, leading them to be called icy dirt balls. Research conducted in 2014 suggests that comets are like deep-fried ice cream, in that the surfaces are formed of dense crystalline ice mixed with organic compounds, while the interior ice is colder and less dense. The surface of the nucleus is generally dry, dusty or rocky, suggesting that the ices are hidden beneath a surface crust several meters thick. In addition to the gases already mentioned, the nuclei contain a variety of organic compounds, which may include methanol, hydrogen cyanide, formaldehyde, ethanol, and ethane, and perhaps more complex molecules such as long-chain hydrocarbons and amino acids. In 2009, it was confirmed that the amino acid glycine had been found in the comet dust recovered by NASA's Stardust mission. In August 2011, a report, based on NASA studies of meteorites found on Earth, was published suggesting DNA and RNA components may have been formed on asteroids and comets. The outer surfaces of cometary nuclei have a very low albedo, making them among the least reflective objects found in the Solar System. The Giotto space probe found that the nucleus of Halley's Comet reflects about 4% of the light that falls on it, and Deep Space One discovered that Comet Borealis' surface reflects less than 3.0% of the light that falls on it. By comparison, asphalt reflects 7% of the light that falls on it. The dark surface material of the nucleus may consist of complex organic compounds. Solar heating drives off lighter volatile compounds, leaving behind larger organic compounds that tend to be very dark, like tar or crude oil. The low reflectivity of cometary surfaces enables them to absorb the heat necessary to drive their outgassing processes. Comet nuclei with radii of up to 30 kilometers have been observed, but ascertaining their exact size is difficult. The nucleus of 322P SOHO is probably only 100 to 200 meters in diameter. A lack of smaller comets being detected despite the increased sensitivity of instruments has led some to suggest that there is a real lack of comets smaller than 100 meters across. Known comets have been estimated to have an average density of 0.6 grams per cc. Because of the low mass, comet nuclei do not become spherical under their own gravity and therefore have irregular shapes. Roughly 6% of the near-Earth asteroids are thought to be extinct nuclei of comets that no longer experience outgassing, including 14,827 Hypnos and 3,552 Don Quixote. Results from the Rosetta and Philae spacecraft show that the nucleus of 67P Churyumov-Gerasimenko has no magnetic field, which suggests that magnetism may not have played a role in the early formation of planetesimals. Further, the allospectrograph on Rosetta determined that electrons above the comet nucleus produced from photoionization of water molecules by solar radiation, and not photons from the Sun as thought earlier, are responsible for the degradation of water and carbon dioxide molecules released from the comet nucleus into its coma. Instruments on the Philae lander found at least 16 organic compounds at the comet's surface, 4 of which have been detected for the first time on a comet coma. The streams of dust and gas thus released form a huge and extremely thin atmosphere around the comet called the coma, and the force exerted on the coma by the Sun's radiation pressure and solar wind caused an enormous tail to form pointing away from the Sun. The coma is generally made of H2O and dust, with water making up to 90% of the volatiles that outflow from the nucleus when the comet is within 3 to 4 astronomical units of the Sun. The H2O parent molecule is destroyed primarily through photodissociation and to a much smaller extent photoionization, with the solar wind playing a minor role in the destruction of water compared to photochemistry. Larger dust particles are left along the comet's orbital path, whereas smaller particles are pushed away from the Sun into the comet's tail by light pressure. Although the solid nucleus of comets is generally less than 60 kilometers across, the coma may be thousands or millions of kilometers across, sometimes becoming larger than the Sun. For example, about a month after an outburst in October 2007, comet Comet 17P Holmes briefly had a tenuous dust atmosphere larger than the Sun. The Great Comet of 1811 also had a coma roughly the diameter of the Sun. Even though the coma can become quite large, its size can decrease about the time it crosses the orbit of Mars, around 1.5 astronomical units from the Sun. At this distance, the solar wind becomes strong enough to blow the gas and dust away from the coma, enlarging the tail. Ion tails have been observed to extend 1 astronomical unit or more. Both the coma and tail are illuminated by the Sun and may become visible when a comet passes through the inner solar system, the dust reflecting sunlight directly and the gases glowing from ionization. Most comets are too faint to be visible without the aid of a telescope, but a few each decade become bright enough to be visible to the naked eye. Occasionally a comet may experience a huge and sudden outburst of gas and dust, during which the size of the coma greatly increases for a period of time. This happened in 2007 to Comet Holmes. In 1996, comets were found to emit X-rays. This greatly surprised astronomers because X-ray emission is usually associated with very high-temperature bodies. The X-rays are generated by the interaction between comets and the solar wind. When highly charged solar wind ions fly through a cometary atmosphere, they collide with cometary atoms and molecules, stealing one or more electrons from the atom in a process called charge exchange. This exchange or transfer of an electron to the solar wind ion is followed by its excitation into the ground state of the ion, leading to the emission of X-rays and far ultraviolet photons. Tails in the outer solar system. Comets remain frozen and inactive and are extremely difficult or impossible to detect from Earth due to the small size. Statistical detections of inactive comet nuclei in the Kuiper belt have been reported from observations by the Hubble Space Telescope, but these detections have been questioned. As a comet approaches the inner solar system, solar radiation causes the volatile materials within the comet to vaporize and stream out of the nucleus, carrying dust away with them. The streams of dust and gas each form their own distinct tail, pointing in slightly different directions. The tail of dust is left behind in the comet's orbit in such a manner that it often forms a curved tail called the Type II dust tail. At the same time, the Iona Type I tail, made of gases, always points directly away from the Sun because this gas is more strongly affected by the solar wind than is dust, following magnetic field lines rather than an orbital trajectory. On occasions, such as when the Earth passes through a comet's orbital plane, and we see the track of the comet edge on a tail pointing in the opposite direction to the ion and dust tails may be seen, the antitail. The observation of antitails contributed significantly to the discovery of solar wind. The ion tail is formed as a result of the ionization by solar ultraviolet radiation of particles in the coma. Once the particles have been ionized, they attain a net positive electrical charge, which in turn gives rise to an induced magnetosphere around the comet. The comet and its induced magnetic field form an obstacle to outward-flowing solar wind particles. Because the relative orbital speed of the comet and the solar wind is supersonic, a bow shock is formed upstream of the comet in the flow direction of the solar wind. In this bow shock, large concentrations of cometary ions congregate and act to load the solar magnetic field with plasma, such that the field lines drape around the comet, forming the ion tail. If the ion tail loading is sufficient, then the magnetic field lines are squeezed together to the point where at some distance along the ion tail, magnetic reconnection occurs. This leads to a tail disconnection event. This has been observed on a number of occasions, one notable event being recorded on the 20th of April 2007, when the ion tail of Encke's comet was completely severed while the comet passed through a coronal mass ejection. This event was observed by the Stereo Space Probe. In 2013, ESA scientists reported that the ionosphere of the planet Venus streams outwards in a manner similar to the ion tail seen streaming from a comet under similar conditions. Jets uneven heating can cause newly generated gases to break out of a weak spot on the surface of comet's nucleus, like a geyser. These streams of gas and dust can cause the nucleus to spin, and even split apart. In 2010 it was revealed dry ice can power jets of material flowing out of a comet nucleus. This is known because a spacecraft got so close that it could see where the jets were coming out, and then measure the infrared spectrum at that point, which shows what some of the materials are. Orbital characteristics. Most comets are small solar system bodies with elongated elliptical orbits that take them close to the Sun for a part of their orbit and then out into the further reaches of the solar system for the remainder. Comets are often classified according to the length of their orbital periods. The longer the period, the more elongated the ellipse. Short period periodic comets. Short period comets are generally defined as having orbital periods of less than 200 years. They usually orbit more or less in the ecliptic plane in the same direction as the planets. Their orbits typically take them out of the region of the outer planets at aphelion. For example, the aphelion of Halley's comet is a little beyond the orbit of Neptune. Comets whose aphelia are near a major planet's orbit are called its family. Such families are thought to arise from the planet capturing formerly long-period comets into shorter orbits. At the shorter extreme, Encke's comet has an orbit that does not reach the orbit of Jupiter, and is known as an Encke-type comet. Short-period comets with orbital periods shorter than 20 years and low inclinations are called Jupiter family comets. Those like Halley, with orbital periods of between 20 and 200 years and inclinations extending from 0 to more than 90 degrees, are called Halley-type comets. As of 2015, only 75 HTCs have been observed, compared with 511 identified JFCs. Recently discovered main belt comets form a distinct class, orbiting in more circular orbits within the asteroid belt. Because their elliptical orbits frequently take them close to the giant planets, comets are subject to further gravitational perturbations. Short-period comets have a tendency for their aphelia to coincide with the giant planet's semi-major axis, with the JFCs being the largest group. It is clear that comets coming in from the Oort cloud often have their orbits strongly influenced by the gravity of giant planets as a result of a close encounter. Jupiter is the source of the greatest perturbations, being more than twice as massive as all the other planets combined. These perturbations can deflect long-period comets into shorter orbital periods, based on their orbital characteristics. Short-period comets are thought to originate from the Centaurs and the Kuiper belt. Scattered disk, a disk of objects in the trans-Neptunian region, whereas the source of long-period comets is thought to be the far more distant spherical Oort cloud. Vast swarms of comet-like bodies are thought to orbit the Sun in these distant regions in roughly circular orbits. Occasionally the gravitational influence of the outer planets or nearby stars may throw one of these bodies into an elliptical orbit that takes it inwards toward the Sun to form a visible comet. Unlike the return of periodic comets, whose orbits have been established by previous observations, the appearance of new new comets by this mechanism is unpredictable. Long-period comets have highly eccentric orbits and periods ranging from 200 years to thousands of years. An eccentricity greater than 1 when near perihelion does not necessarily mean that a comet will leave the solar system. For example, Comet McNaught had a heliocentric oscillating eccentricity of 1.00019 near its perihelion passage epoch in January 2007, but is bound to the Sun, with roughly a 92,600-year orbit because the eccentricity drops below 1 as it moves further from the Sun. The future orbit of a long-period comet is properly obtained when the oscillating orbit is computed at an epoch after leaving the planetary region, and is calculated with respect to the center of mass of the solar system. By definition, long-period comets remain gravitationally bound to the Sun. Those comets that are ejected from the solar system due to close passes by major planets are no longer properly considered as having periods. The orbits of long-period comets take them far beyond the outer planets at aphelia, and the plane of their orbits need not lie near the ecliptic. Long-period comets such as Comet West and C. 1999 F1 can have aphelion distances of nearly 70,000 astronomical units with orbital periods estimated around 6 million years. Single apparition and non-periodic comets are similar to long-period comets because they also have parabolic or slightly hyperbolic trajectories when near perihelion in the inner solar system. However, gravitational perturbations from giant planets cause their orbits to change. Single-apparition comets have a hyperbolic or parabolic oscillating orbit which allows them to permanently exit the solar system after a single pass of the Sun. The Sun's Hill sphere has an unstable maximum boundary of 230,000 astronomical units. Only a few hundred comets have been seen to reach a hyperbolic orbit when near perihelion that, using a heliocentric unperturbed two-body best fit, suggests they may escape the solar system. No comets with an eccentricity significantly greater than 1 have been observed, so there are no confirmed observations of comets that are likely to have originated outside the solar system. Comet C. 1980 E1 had an orbital period of roughly 7.1 million years before the 1982 perihelion passage, but a 1980 encounter with Jupiter accelerated the comet, giving it the largest eccentricity of any known hyperbolic comet. Comets not expected to return to the inner solar system include C. 1980 E1, C. 2000 U5, C. 2001 Q4, C. 2009 R1, C. 1956 R1, and C. 2007 F1. Some authorities use the term periodic comet to refer to any comet with a periodic orbit, whereas others use it to mean exclusively short-period comets. Similarly, although the literal meaning of non-periodic comet is the same as single-apparition comet, some use it to mean all comets that are not periodic in the second sense. Early observations have revealed a few genuinely hyperbolic trajectories, but no more than could be accounted for by perturbations from Jupiter. If comets pervaded interstellar space, they would be moving with velocities of the same order as the relative velocities of stars near the Sun. If such objects entered the solar system, they would have positive specific orbital energy and would be observed to have genuinely hyperbolic trajectories. A rough calculation shows that there might be 4 hyperbolic comets per century within Jupiter's orbit, give or take 1 on perhaps 2 orders of magnitude. Oort cloud and Hills cloud. The Oort cloud is thought to occupy a vast space from somewhere between 2,000 and 5,000 astronomical units to as far as 50,000 astronomical units from the Sun. Some estimates place the outer edge at between 100,000 and 200,000 astronomical units. The region can be subdivided into a spherical outer Oort cloud of 20,000 to 50,000 astronomical units, and a donut-shaped inner Oort cloud of 2,000 to 20,000 astronomical units. The outer cloud is only weakly bound to the Sun and supplies the long-period comets to inside the orbit of Neptune. The inner Oort cloud is also known as the Hills cloud, named after J. G. Hills, who proposed its existence in 1981. Models predict that the inner cloud should have tens or hundreds of times as many cometary nuclei as the outer halo. It is seen as a possible source of new comets to resupply the relatively tenuous outer cloud as the latter's numbers are gradually depleted. The Hills cloud explains the continued existence of the Oort cloud after billions of years. Exocomets beyond the Solar System have also been detected and may be common in the Milky Way. The first exocomet system detected was around Beta Pictoris, a very young A-type main sequence star, in 1987. A total of 10 such exocomet systems have been identified as of 2013, using the absorption spectrum caused by the large clouds of gas emitted by comets when passing close to the star. Effects of comets. Connection to meteor showers as a result of outgassing. Comets leave in the wake a trail of solid debris too large to be swept away by radiation pressure and the solar wind. If the comet's path crosses the path the Earth follows in orbit around the Sun, then at that point there are likely to be meteor showers as Earth passes through the trail of debris. The Perseid meteor shower, for example, occurs every year between 9 and the 13th of August when Earth passes through the orbit of comet Swift-Tuttle. Halley's Comet is the source of the Orionid shower in October. Comets and impact on life. Many comets and asteroids collided into Earth in its early stages. Many scientists think that comets bombarding the young Earth about 4 billion years ago brought the vast quantities of water that now fill the Earth's oceans, or at least a significant portion of it. Other researchers have cast doubt on this idea. The detection of organic molecules, including polycyclic aromatic hydrocarbons, in significant quantities in comets has led some to speculate that comets or meteorites may have brought the precursors of life, or even life itself, to Earth. In 2013 it was suggested that impacts between rocky and icy surfaces, such as comets, had the potential to create the amino acids that make up proteins through shock synthesis. In 2015, scientists found significant amounts of molecular oxygen in outgassings from comet 67P, an indicator that presence of that molecule may occur naturally more often than it had been thought, and thus that it may not be as strong an indicator of alien life as has been supposed. It is suspected that comet impacts have, over long time scales, also delivered significant quantities of water to the Earth's moon, some of which may have survived as lunar ice. Comet and meteoroid impacts are also thought to be responsible for the existence of tektites and astrolites.